I'm going to be talking about converse bounds in certain optimization problems, particularly optimization based on Gaussian processes. I imagine this is not necessarily the most familiar topic, so I'm going to probably spend a lot of the talk sort of introducing the problem and going over some existing work. So here's the basic problem, Blackbox optimization. I mean, this is just about as generic as it gets. We want to maximize some function over some domain, which we call D. What I mean by black box is that we don't really have any sort of description of the function. So in particular, we don't have things like gradients. We can't use our nice gradient descent, or in this case, gradient ascent, because all we have is we can give an input and we get out a noisy output. And that's all we can do. In addition, we assume that every time we query the function, it's actually very expensive. So we'd really like to query the function as few times as possible. And I'll give examples of why it might be expensive in a second. We're going to look at two different sort of performance measures. One is maybe more familiar, which is you query a bunch of points, and then you declare one point that you think is good, and you're interested in how close you are to optimal. So this X star is the true maximum. You got something which is maybe a bit below the true maximum, and this difference is called the simple regret. Another one, which is very popular in the bandit literature, is cumulative regret. That's where it's not just about one final point that you picked, it's about every point that you picked along the way. So sort of generally speaking, an example of this might be if your function is measuring like user clicks on advertisements. In that case, every time you display an ad, you see if a user clicks, every click really matters. Whereas the simple regret one, I think I have some examples here. The simple regret one might be for something more like parameter tuning, which is actually one of the big uses of this sort of problem recently. People are trying to automate the process of tuning, for example, hyperparameters in their deep neural network or robotics parameters. And the way they do that is by somehow introducing some model on the function and trying to use these algorithms that hopefully get close to the true maximum. There's all sorts of other applications as well. I'll mention that this Gaussian process method, which I'll introduce in a second, was actually used in this famous AlphaGo program, which was developed here in London. Okay, so here's a picture explaining why this might be a difficult problem. If we've queried a bunch of points, even if we don't have noise, so just assume these are noiseless points that we've observed of the function. So we could imagine the function looks something like this, but then of course there's other maybe perfectly equally plausible explanations, maybe something like this. And then who knows, maybe it's something very bizarre like this. So clearly, to be able to say anything here, we somehow need to put limits on how ugly things can get. And in other words, we'd like to have some sorts of smoothness assumptions on the functions we're optimizing. I think I forgot to mention, regarding this idea of queries being expensive, the example is if you're tuning hyperparameters, then querying a function might be testing how good those parameters are, and that's like training a whole neural network, which takes a very long time. In other applications, querying the function might actually be running a real-world experiment, so these queries might be really expensive. We'd like to have few queries. Okay, so as the title suggested, we're going to model smoothness using Gaussian processes. These are very widely used both in theory and practice. It's actually, at least the model I'm introducing initially is a Bayesian model, where we say that the function is modeled as being random with some prior distribution. And the prior distribution is a Gaussian process, which is essentially a stochastic process where any finite set of samples, if you look at that joint distribution, it's jointly Gaussian. And much like a Gaussian is specified by its mean and variance, the Gaussian process is specified by a mean function, what's the mean of f of x, and a covariance function, which is going to be referred to as a kernel. So K, you can think of K is for kernel, but whenever I say kernel, if you haven't heard that terminology, just think of a covariance function. And that's between 2 points, f of x and f of x prime. So if we're on a finite domain, this is actually nothing special. It's just a multivariate Gaussian with some covariance matrix. But here, we're probably thinking more about continuous domains, where this is maybe a bit less familiar. Okay, so I think I've mentioned this. It's fully specified by the mean and covariance. We're actually going to focus on the zero mean case. If you knew what the mean was, then you could actually just subtract it off. So if you're sort of saying that you know the prior, then you could say this is without loss of generality. Actually, choosing a good covariance function or kernel is actually a very hard task, but it's not really the focus of this talk. So for this talk, you can think of this covariance function as being known. Here are a couple of popular examples. So typically, if you're going to have smoothness, then you're going to say closer points have more correlated function values, and further away point has maybe uncorrelated or nearly independent function values. And this is modeled by things like the squared exponential, where we see that the correlation decays with distance, in this case, exponentially, or e to the minus distance squared. And we have this parameter L, which is like the length over which the function is varying. Another popular one is the Matin kernel, which has a parameter nu, which sort of indicates the smoothness. If nu equals 1, we get something less smooth. We have like a heavier tailed decay. And as nu goes to infinity, we actually sort of recover this first squared exponential kernel. And then there's all sorts of different smoothness in between. So here's an example of a random draw from a Gaussian process from these two different kernels. And we can actually model all sorts of different behavior as well. We can model like periodic behavior, linear, quadratic. So it's a fairly rich modeling class to assume a Gaussian process model. And it's also nice sort of mathematically, so this is perhaps why it's been popular. Okay, so yeah, to expand on this thing of being nice mathematically, one of the particularly nice things is that we can actually explicitly compute a posterior distribution given points that we've sampled. So we have, you can think of it as the Gaussian process model is a prior distribution on F. Let's suppose we have Gaussian noise because it makes things nice. And if we query some points and observe their corresponding samples, the posterior distribution is a Gaussian process. These equations may or may not be familiar. This is the posterior mean. And if you substitute x equals x prime here, you can think of this as posterior variance. And instead of worrying about the equations, maybe just worry about this picture here. So let's suppose this blue one was the actual underlying function, and we're sampling from it. So we sample a point. And what I'm plotting here is in the dashed line, the posterior mean, and the gray region is posterior mean plus or minus a few standard deviations. So when we sample a point, because of the smoothness, we become like quite confident about the function around that point. And the idea is if we sample a few points, we could start to get a better idea of what the function looks like, and we could try to hopefully steer our samples towards the function maximum. So we learn more, our sort of mean plus or minus standard deviations starts to shrink. This gray region is shrinking. And then eventually we see the samples are going towards the maximum, and this is sort of the idea used for optimization. And one of the big advantages of Gaussian process is they do tend to be the most sample efficient of the methods in the literature. So there's alternatives like genetic algorithms and so on, but Gaussian processes have really been sample efficient, so they're good for these problems where sampling the function is really expensive. So let me just name one algorithm. There's a whole bunch of algorithms from the literature. I'm going to name one because it's one where some theoretical bounds are known. So the idea is to take this gray region, which was mean plus or minus a few standard deviations, and call the upper and lower parts of the gray region the lower confidence bound and upper confidence bound. And if this few standard deviations was enough standard deviations, then the function actually will lie in that interval with high probability. And so with high probability, we actually have that the function is always between the lower and upper confidence bounds. In other words, it's always in the gray region in this picture. Then the algorithm is quite simple. It's not just used here. It's been used classically in many types of bandit problems or optimization problems, which is to choose the next point to maximize the upper confidence bound. And the principle behind this is optimism under uncertainty. So if you are uncertain of something, maybe to give a bit of a real-world example, if you're looking for the best restaurant in London, say, and you've got one which you're quite confident that it's okay, and then you've got another one which may be great or may be terrible, this says, be optimistic and try it out, because if you don't try it, you might miss you might miss a good opportunity, and you might fail to find the function maximum. So it's optimism under uncertainty, and it's a very simple decision rule on how to choose the next point. And it has some theoretical guarantees. I won't spend too long on these because I want to focus more on the lower bound. But it says that if you will get within epsilon of the optimal after the time satisfies this, so it sort of looks like the time is behaving as 1 over epsilon squared, but it's a bit more subtle than that because we've got these other terms depending on t as well. The main other term is this gamma t, which is actually a mutual information quantity, which sort of captures this, how smooth or how nice the kernel is. So it tends to be lower when you've got very smooth functions and higher when you have very erratic functions. So to go back to these two examples, you can get scaling behaviors like 1 on epsilon squared times the log factors for this smooth squared exponential kernel. The Matten kernel is less smooth, so you tend to get something more like 1 over epsilon cubed or 1 epsilon to the 4, depending on the sort of dimension d and the smoothness parameters. There's been similar guarantees also for the cumulative regret. This is the one where every point matters. So you really want to make, you'd want every point to have a high function value, and you're summing up the regrets of every point. And you'd like this to be sublinear in t. So it's sort of square root t times these other terms. Again, this mutual information quantity. And these are the examples. We can get things like square root t times log, or we can get things like maybe t to the power of 2/3 or t to the power of 0.9, depending on the parameters of that kernel. Okay, and the last thing I'll say before I get on to the main thing I want to talk about is non-Bayesian setting. So perhaps we don't like placing exact priors, and especially assuming that they're known, because sometimes your Bayesian algorithm might be very sensitive to a mismatched prior. And in fact, that is often the case here. So if you're not a fan of Bayesian, the good news is we can use the exact same algorithm in a non-Bayesian setting. So we can basically construct the same types of confidence bounds and use the same algorithm which maximizes the upper confidence bound. The model's a bit more difficult to describe. It's saying that the function is in some class fk, and this is a bit of a description of the class. It's called a reproducing kernel Hilbert space, KHS. So it's basically defining a Hilbert space on the function. The Hilbert space has a norm depending on the kernel, and you're saying that the function has a low norm. We can write down the norm explicitly if we think about Fourier transforms. So we can take the Fourier transform of the function. If the kernel is stationary, meaning it only depends on the difference, then we can take the Fourier transform of the kernel as well. And then the function norm is essentially an L2 norm in Fourier space, but normalized by the kernel. So this is getting a bit technical. Don't have to worry too much about this. Just think of this as a convenient deterministic function class where we can still use these nice Bayesian methods and get these sorts of same guarantees. How long have I been talking? 5 left?
No, so 5, 6.
Remaining, okay. Okay, so I've spent a fair bit of time. I'll now talk about my own work on the lower bounds, converse bounds. So we had these upper bounds for a while, and they're kind of nice to have. But if we don't have any sort of lower bounds to complement them, then we really are a bit in the dark of how much better we can do. So perhaps there's another algorithm out there that can get much lower regret bounds than these existing upper bounds. So of course, this is information theory. I guess I don't need to motivate converses too much. We started with the non-Bayesian setting. Non-Bayesian tends to be a bit nicer for lower bounds because you're sort of looking at the worst case over a function class, and you can always lower bound the worst case by the average case. And I'll talk about that in a second. These are the sorts of results that we got, looking a little bit like what we saw before. And in fact, for the squared exponential, we're matching up to maybe a log factor. So this is not quite like communication where you get really nailing down the constants, but at least we can get good scaling laws. For the Matten kernel, there are actually still gaps, even in the scaling laws. And I suspect it's the lower bound that's tight and the upper bound that needs improving. But I won't go too much into that. And similarly for the cumulative regret, where every point matters, we again nearly match for the squared exponential, and we have some gaps remaining for the Matten kernel. So the proof, it gets quite tricky, but I'll try to give some high-level ideas. And yeah, following a lot of works in sort of statistical estimation and more recently in optimization, we're kind of trying to review the optimization problem through the lens of multiple hypothesis testing. So we like multiple hypothesis testing because we can use things like Fano's inequality. We're used in communication. So in this picture, these gray boxes are the things that are fixed. We're doing a lower bound, so we're assuming there's a fixed algorithm, which is sampling the function. Then it's outputting maybe the final point that it thinks is nearly optimal. We then introduce a couple of extra blocks, which are sort of artificially induced for the purpose of analysis, to basically reduce to multiple hypothesis testing. We imagine an index choosing some function, and then we imagine someone at the end trying to get back that index. And we basically show that if the algorithm is good, we can actually get back the index if we've chosen these difficult functions appropriately. And then we can say that successful algorithm means successful hypothesis test. We can sort of flip that around and say that if we can't do multiple hypothesis testing, then we can't have had a successful algorithm. So this is a basic reduction that's been used throughout many aspects of statistics. It's often used with Fano's inequality, but that didn't work well here. In these adaptive problems, the mutual information just gets often nearly impossible to characterize. So Fano's inequality didn't work so well, but I'll tell you what we did use. And first I'll tell you what function class we used. So we constructed a subset of functions, a finite subset of this function class which still captures the difficulty. And we chose each function to just have a single peak and then to basically decay. And this is a rather low peak. It's a peak of, we just parameterize it by epsilon. So the idea is that if you're claiming to be within epsilon of optimal, you can only be within epsilon of optimal for one of these functions. So if you successfully got within epsilon, you must be able to identify the function. And that's what we wanted to do on this slide. So yeah, this is what our function class looked like. Basically, how narrow we could make these was sort of dependent on the kernel. So we get this kernel dependence coming in, which I won't go into. Basically, the key tool that's used in place of Fano's inequality is something going back to LeCam in statistics. So this is a very basic inequality, almost just by definition of total variation. We can bound the probability of two events in terms of P0 and P1 in terms of the total variation between them. This is a slight variation where we instead bound the expectation of a function in terms of, well, okay, then you can use Pinsky's inequality, upper bound total variation by relative entropy or KL divergence. So then the idea is that this P1 is going to be the actual sort of sampling distribution under one of these functions. Say this function here, we have a distribution when we create a point. We have a corresponding distribution of what we're going to observe in the noisy sample. We let this P0 be a so-called null distribution where everything is just 0. So essentially what we're doing is we're saying that all of these functions are nearly 0. So in some sense, they're hard to distinguish from the 0 distribution. If the actual distribution were corresponding to a function of all zeros, then we couldn't possibly learn anything. And so, yeah, essentially something is hard to do under this null distribution. The distributions are close in KL divergence, so it must be hard to do under the true distribution. This is basically the rough idea. And we could choose this, this function a of y here to be either cumulative regret or simple regret. So it's a very rough overview of the proof. Okay, I'll just wrap up. We also handled the Bayesian setting. So Bayesian setting, we basically showed that under some conditions, the regret is always, cumulative regret is always square root of t. I looked at one dimension because this was a little bit tricky, and I think we could extend this to any constant dimension, but I just started with one dimension, which was already challenging enough. So in the Bayesian setting, we can't really choose a finite subset of hard functions because we're not doing like a worst case. It's an average case. We don't have control of saying sort of lower bounding the worst case by the average. We're stuck with the average that we were given within the Bayesian setting. But what we can do is sort of, if we're looking at stationary kernels, we could say that if we slightly shift the function, then both of these functions have essentially the same quote-unquote probability of occurring. And then we can use a Gini argument where we actually just tell the algorithm one of these two is the function. Then it sort of comes down to a binary hypothesis test, and we can use similar ideas to what I said. And in this case, actually, Fano's inequality did work out well, despite being this similar sort of adaptive problem. So, you know, sometimes Fano's inequality seems to work, sometimes it seems to just not be so suitable. Okay, so here's a summary of the bounds. I'd say the squared exponential the scaling laws are now fairly well understood. There's still some open problems in the MATM kernel. And perhaps in the Bayesian setting, there's a bit more to do as well. For references, these are the two papers on the non-Bayesian and Bayesian settings. And if anyone wants to learn more about Gaussian processes in general, these are some tutorial slides. So thank you.
Next speaker.